Uh, Today we will be discussing on a very interesting concept called a chip for drug screening. Alright. So, if you recall that one of the in one of the lectures I have discussed that what is the problem right now in screening a particular drug. For the given 3 drugs, which drug to give to a patient so that the patient can recover faster. All 3 drugs, assuming that they are of the same cost, all are FDA approved and all are meant to kill that particular disease, right. How the clinician will come up with an idea or with a intervention that which one he or she has to prescribe to for a particular patient. Now, can we design a chip that can screen this drug for a given patient? What does I mean? Suppose you take example of a disease where you can take the cells of the patient, and if you see the screen, I'll tell you more about that. So, right now what happens is that the cells are taken, right, and then they are grown to form a tumor, and then there is a chemotherapy, and if the chemotherapy is effective, then initially the cells would start dying, tumor will reduce, but after some time this tumor will regrowth. Alright. So, it is very important to identify which drugs are susceptible or tolerant or for that particular tumor. Now, what we want to work on is, if you see a tumor, right, tumor is always surrounded by something called extracellular matrix, okay, is called ECM, extracellular matrix. This is your tumor. Alright. Now, how to replicate this tumor and extracellular matrix? This is in vivo within the body. How to replicate this condition onto the microfluidic chip such that we can use the platform for drug screening. So, for that what we will do is, this ECM that I was talking about, right, ECM can be replaced by Matrigel, right, ECM can be replaced by Matrigel. One thing. Second thing, if I have a microfluidic chip like this, and below it, if I magnify this particular section, then this is like interdigital electrodes are there below the chip, like this. This is this particular section. Okay. So, now you have interdigitated electrodes. I will load the cells, onto this particular platform with Matrigel. So, cells with Matrigel, alright. So, cells would be here with Matrigel, from where you get the cells? Cells from the patient, right. If I have cells with the Matrigel on this particular interdigital electrodes, I can measure impedance called Z, right, and in this channel we can flow continuously drug with media, right. Drug with media is like as if you are giving a drug to the blood and blood flows through the channel, alright. Now, let us understand how this works. So, if you have the chip and you have 3 of this, then you can test 3 different drugs for the given patient, is not it. So, you see this particular schematic, the green one is where you load the cells with Matrigel, the red one is a drug that can flow. Now, for the given patient you can test 3 different patients for this particular chip, right, because you have cells for patient 1, cells for patient 2, cells for patient 3, and you have a single drug that you are flowing. But like I was drawing earlier, you can test different drugs for same patient. That means that if I have this one, which is my first microfluidic chip, right, like this, and then another microfluidic chip like this, and then third one like I am showing in the figure, right. And if I load cells here here and here, then I flow drug 1 here, drug 2 here and drug 3 here. What will happen is, so if I zoom this particular part, it will look like this, okay, it will look like this. That means the material is sitting on material with cells are sitting on the interdigitated electrodes. When that happens, there is a impedance Z1. In this case it will be Z1, in this case it will be Z2, in this case it will be Z3, Z1, Z2, Z3. Okay. Now, when I flow drug, the drug will diffuse into this particular material and it will start killing the cells based on the efficacy of the drug. How much drug is efficient? If drug is efficient, then the cells would start dying. When cells start dying, I will have Z11, Z21, Z31. Now, the impedance would change based on the conductivity of the media, right. The conductivity of the medium would change if the cells dies more. If the cells dying is called lysing, and when cell lyses, the conductivity would increase and impedance would decrease. That means if I flow drug on this particular 3 channels, right, drug 1, drug 2, drug 3 for 24 hours, and if I see a larger change in impedance values, then for the one which is showing the more conductive more conductivity, I can use that as a drug for a given patient rather than drug 1 or drug 2. For example, if drug 3 shows higher conductivity or higher change in impedance values compared to drug 2 and drug 1, then drug 3 would be more effective for the given patient. For the second patient, it may not be true. Again, you have to do the same experiments and you may find that instead of drug 3, drug 2 may be useful. Now, how these interdigital electrodes can be fabricated is very simple. I have taught you earlier, and the right side is a schematic of one such interdigitated electrodes, right, with 5 micron spacing. These lines that you see here, 5 micron spacing and 5 microns width. Alright, and these are finger electrodes or interdigital electrodes that we have fabricated, very clearly defined interdigitated or finger lines are there, and this chip can be used for screening of drugs. You can see here that if I take an example of breast cancer cells versus a prostate cancer cells, then only gel, there is no change, gel plus drug. When you have gel plus drug on the channel, there is no change, gel plus cancer cell, no change, gel plus cancer plus media flow, no change, but only when there is a gel plus cancer cell on static platform and when you flow on dynamic platform, then you have change. What is static platform? You take a chip, you load the material everywhere and you load cells like this, you load lot of cells like this, okay, and then you load this thing with some kind of drug. Now, this drug is in continuous contact with the cells. When the drug is in continuous contact with the cells would die. But this is a static platform, our body is not static, our body is dynamic, and that is why we had to rely on dynamic platform instead of static platform, and that is why we had to go for a microfluidic platform. So, you can still see that when you flow the drug, then drug plus cancer cell plus, in a dynamic mode is showing a different value. For also prostate cancer, it shows a different value compared to the static platform, and that is why we have to rely on a dynamic platform. Also, this is very good because we can get something around 14 hours, we get all the understanding about the efficacy of the drugs. So, it is worth trying this platform as a patient centric platform. For prostate cancer, we have used paclitaxel as one of the drugs, and for breast cancer we have used carboplatin as one of the drug. Now, you know that the cells needs to be alive when you do not flow the drug, right. So, for that you have to have a incubation medium, and for that you can have a heater and then interdigital electrode. So, if I draw this a block here, then the video block is a glass, then there is a heater, then there is an insulator which is SiO2 on which there are interdigitated electrodes and microfluidic platform. Alright. So, this is how the microfluidic chip can be fabricated for drug screening. It's a we can also name it as a patient centric platform, and this is the end of this particular module, right. So, what we have learned till now is how can you design a microfluidic platform with the help of electrical sensors for drug screening. And I have just shown you the breast cancer cells versus prostate cancer cells, but the people have used for a lot of other applications. Alright. So, till then you take care. If you have any questions, you let me know through the medium, right. We have a beautiful forum through which you can ask a lot of questions, and again, if you have really important question, you can also shoot me an email. Alright. So, I hope that overall you like this sensor actuators course, and you are getting some new concepts into your understanding, right, where you can use it for several different applications, starting from drug screening to gas sensors to force sensors, atrial fibrillation, EMT sensors, which is electrical, mechanical and thermal sensors, right. We have seen piezoresistors, we have seen interdigital electrodes, and we have seen a lot of lab components. Alright. And there are a lot of assignments. I hope that you do not miss any assignments. Very important part of the course is to go for the assignments, and if you have registered for the course and if you registered for the exam, then you take this course. Believe me, the exams set, the questions that I have said is not that difficult. Alright, it is all through the things that we teach here, and some of course is about thinking, right. If I give you an example that if I use a positive photoresist and negative photoresist, and if I have a bright field mask, right, what do you expect as the outcome? Then you can understand that positive photoresist, when you whether the area which is not exposed will get stronger, while in negative photoresist the area which is not exposed will get weaker, right. So, based on that, how you can think, that is just I am giving you an example. Okay. So, the point is, once you understand the sensors and actuators part, you can use it for several applications. I have talked about some thing on the medical side, but you can use it for space, you can use it for a lot of other applications, including your mobile telecommunications, TV, right, displays that you use it in a daily routine, mobile phones and automobiles and lot of other places, right. So, this is my last class. If you have any questions, again feel free to ask me through NPTEL forum, right. I will see you in some other course. Till then, you take care, have a nice year, right, wherever you are, and be safe. Just go through each module, right, and all the best for your exams.